Welcome back, Calculus. We are just going to start Unit 2 today. The objective for today is going to be to determine graphically whether a function is differentiable or not at a point. So I'm going to force a pause on your screen. Please double check the checklist, and then we will continue. Alright, so here is our table of contents for Unit 2. You can see the three due dates we have for this unit, a little bit longer than Unit 1. So I'm going to force a pause on your screen so that you can copy what you need to in your table of contents and that you have all the due dates ready to go. Alright, so just a couple notes for Unit 2. I do get pickier about showing work with Unit 1. There is a lot of leeway because I know quite a bit of that. I understood you could do in your head, but for if you want the plus for each assignment, then do be mindful about showing work. Virtual students, if you get stuck on a question, please go to the discussion tab on Canvas and ask your question there. You are going to receive a little quiz grade for asking at least 2 questions and answering 2 questions throughout Unit 2. And then remember, especially my face-to-face students, when you start your homework, label it and then highlight, where your homework starts and where your notes end so that I can find that easily. Alright, so I have this red graph on the screen. Hopefully you can see it here. What would you say this is a graph of? Alright, I'm going to jump down here so I can have my zoom buttons ready. So right now this looks like a horizontal line through the y-axis at 0, right? It looks like y equals 0. If I zoom out, if I continue to zoom out, are we seeing some curvature there? Yes. Doesn't really look like y equals 0 anymore, right? Let me hit the home button. Ah, does that graph look familiar? Yeah, this is actually y equals x squared. However, as I zoom in enough, the graph started to look linear, right? And in fact, that's the case no matter what value I pick. So if I choose to zoom in here at like 1, 1, look, if I zoom in enough, now it looks like a linear function, okay? And this is actually a key concept of calculus. It's what we call differentiability. So differentiability simply means if I zoom in enough, my function starts to look like a linear function. All right, let's try another one. Let's come back to my home screen. What is that function? So here, this is not a trick question, this is y equals the absolute value of x. So what I'm going to do is choose the origin here, once again, and let's see what happens when I zoom in here. So as I zoom in, do you see that it's not looking like a linear function to me? What's happening? Are we ever able to get rid of that corner? That corner just keeps staying with us no matter how much I zoom in. So I can zoom in, zoom in, zoom in, zoom in, and I just cannot get rid of that corner, right? So what we say is this function is not differentiable at x equals 0 because no matter how much I zoom in, I am not getting a linear function, right? I just keep getting that corner. Now if I were to pick any other point, like let's say point over here, maybe 6, 6. If I zoom in, oh, it's nice and linear there, right? It's linear, it's differentiable everywhere except for the origin, okay? So absolute value of x is differentiable everywhere except where? Except the origin, or at x equals 0. All right. All right, so I've got 3 graphs on the screen for you. Each of these 3 graphs fails to be differentiable at least in one place, okay? Again, what does it mean to be differentiable? It means that if I zoom in enough, the slope exists there. In other words, it looks like a linear function if I were to zoom in enough, okay? So take a look at the graph on the left there. Where do you think I'm going to have some problems? So I'm going to have problems at x equals -1 and +1, because if I zoom in enough, what's going to happen is it's going to start to look like a vertical line, and a vertical line is not a linear function, right? That's slope undefined. We call this a cusp, very similar to the corner of y equals absolute value of x, right? Okay, how about the second graph, the one in the middle? This one's going to have a problem here at x equals 3, if you can tell there, because again, when I zoom in right there, what's it going to look like? It's going to look like a vertical line, right, which is not a linear function. Vertical lines have slope undefined, okay? Where do you think the problem is for that last graph? The problem is here, when I zoom in right there at x equals 1, what am I going to get? I'm just going to get empty space, or here I'm just going to get a dot. In either case, it is not going to look like a linear function. So this function fails to be differentiable at x equals 1. All right, I'm going to force a pause on your screen. Can you copy what I have, and then we'll fill it in together. All right, so what do we think the conditions are for a function to be differentiable? And don't be scared about that word. It just means that the slope exists there. So in order to be differentiable at x equals c, we'll notice we certainly, from this example, have to be continuous at c, right? So let's write that. So first of all, f must be continuous at x equals c. Okay, but it was not enough for f to be continuous, right? Because if I take a look at these first two graphs, they were both continuous, but they failed to be differentiable at a few points, right? So in addition to being continuous, we also have to have our function be what mathematicians called smooth, okay? So f must be smooth, and that means when I zoom in enough there, that function starts to look like a linear function. In other words, no corners, no cusps. We're going to look at that a little bit more as well. No vertical tangent lines. Okay, so go ahead and write that, and then let's take a look a little bit more at those cusps and vertical tangent lines. All right, so here I have graphed y equals x to the 2/3 power. Notice that if I pick any x value other than at the origin, it starts to look linear, okay? So it's nice and differentiable everywhere except let's take a look at the origin, okay? So what happens as I start to zoom in there? Center this again. So as I start to zoom in, look there, it looks like a vertical line, right? And does vertical line have a defined slope? No, vertical line has undefined slope, so it is not a linear function, so it doesn't pass the vertical line test, so we have a problem there at the origin. So again, this function was differentiable everywhere except what we call that cusp. So cusp, it looks more like this, almost like the beginning of a heart, and a corner is more of a sharp turn, okay? Like y equals absolute value of x, okay? How about this function? This is y equals x to the 1/3 power. Again, nice and differentiable everywhere except the origin, because look, when I zoom in on the origin, once again, we start to get that vertical line, right? And again, vertical lines do not have defined slope. So that's why we have to be really careful. In addition to be continuous, we need to make sure we have no corners, no cusps, and no vertical tangent lines, like that guy. All right, so again, what are the two conditions we need for a function to be differentiable at a point? Yep, we need the function to be continuous, first of all, and then if it's continuous, we also need for it to be smooth, right? Now, if a function's not continuous, there's no way for it to be differentiable, all right? So as a reminder, let's talk about the three conditions to be continuous at a point, x equals c. Remember, we need f of c to exist. We need the limit as x approaches 2 of f of x to exist. And then we need the two to be the same, right? We need the function value to equal the limit. All right. Okay, so what I'm going to do is work a couple from your homework. Make sure you feel good about those. And then again, if you're a virtual student and have a question, please put your questions in the discussion tab. All right, so this is question 1A from your homework, and notice that the first few questions just deal with continuity, okay, not differentiability yet. So this question just says, determine if the function's continuous at the indicated value of c, in this case -1, and if not, which of the three conditions fails, okay? So would you say that this function is continuous at x equals -1? No, I'd have to pick up my pencil there. So not continuous. So then we have to decide which of the three conditions fails, and we just kind of go in order. So does f of -1 exist? It does. All right, I have that closed circle right there. Okay, what about the limit? Does the full limit exist at -1? It does not. Look, you have a jump, right? So the left and the right exist, but they're not the same. So that's the condition that fails. So we're just going to say the limit as x approaches -1 of f of x does not exist. All right, same directions for part B. Go ahead and try this one on your own and then click continue when you're ready to see the answer. So this one's not continuous either. Notice that f of 3, the function value, does not exist. All right, so let's move on to question 8 from your homework. These directions say determine whether the function is continuous, differentiable, both, or neither at the indicated value of c. So let me first ask you this. If a function is continuous, is it automatically differentiable there? No, it is not, right? What about if it's differentiable, is it automatically continuous? Yes, it is. Now, can a function be differentiable but not continuous? No, it cannot. So if it's differentiable, it's automatically continuous, right? Okay, so let's take a look at the indicated x value here. So x equals c. So I'm looking at that part of the graph. Would you say that this function is continuous at x equals c? Yeah, I can draw it without picking up my pencil, right? What about differentiable? Is it differentiable at x equals c? It is not differentiable, right? There's a corner there. In other words, the slope coming from the left is not the same as the slope coming from the right. All right, you try part B. Decide if this is continuous, differentiable, both, or neither at C, and then click continue when you're ready to see the answer. All right, this is neither continuous nor differentiable. I see that there is a hole there, so I'd have to pick up my pencil to draw it, so it's not continuous. And if it's not continuous, it is automatically not differentiable. All right, that is it for this lesson. Go ahead, for my virtual students, go ahead and continue the 2.0 assignment, and I will see you all next time.